because there are 3 elements that can occupy level 0 and level 1. So the number of, if the height of the tree is 2, then there must be at least one element in the last row. So n should be greater than 3, but it should be less than 7, because 7 is the maximum that can fit into these 3 levels: 1, 2, 3, 4, 5, 6, 7. And we can see that this is actually satisfied because n is 6 here. So 6 is less than equal to 7 and also greater than 3. So we're still in the definition of a heap here. Uh, so the shape, so a heap has two properties. It is a complete binary tree, and that's called the shape property. And the second property of the heap is called the heap property. And what this says is, we are actually going to look at something called a max heap here. A max heap is a heap that is going to support this particular operation, remove max. Okay, so I'm going to define a max heap here. The heap property is that if I look at any node, if I look at any child of this node, so let's say the value of the key here is k, the value of these two elements must be less than or equal to k. Okay, so the key value of parent must be greater than equal to the key value of all children. So if you go back to this example, 8 is greater than 4 and 8 is greater than 6. So the heap property is satisfied here. 6 is greater than 5 and it's greater than 1. So the heap property is satisfied here. 4 is greater than 3. So the heap property is satisfied here. So if you take any path from the root down to the leaf, the key values should be non-increasing. Okay, they can, ordinarily they'll be decreasing, but if you allow for multiple items with the same key, then you could have uh, a parent and a child having the same value for the key, but it can't increase down down this path. It's going to be non-increasing, or you can say it's going to be decreasing, not necessarily monotonically decreasing, but decreasing. So that's why it's called a max heap, because if you want the, so here's a consequence of having this heap property. Where is the maximum item, where is the maximum key going to be present in a heap? If you look at this, tree here, it is actually a heap. It satisfies the shape property as we've seen, and it also satisfies the heap property that we've seen. So this is an example of a heap. Where is the maximum element located here? It's located at the root. And that's not a coincidence. It's a direct consequence of the heap property. Because let's say the maximum element was present somewhere else. Let's say it was present, say, somewhere here. That wouldn't have been possible, because then if you had looked at its parents, the values of the parents, as I go up this path to the root, should have been increasing, or at least non-decreasing. So the value of this node and this node must be at least as big as the value of this node. So this node can't be the maximum then. Right? So the maximum value of any item is going to be found in the root. Yeah, yeah. Uh, but they're not sorted here. 5, 1, 3. Yeah, that's the coincidence. Actually, this is not sorted in decreasing order, right? It's 5, 1, and then 3. So it's not sorted in decreasing order. It's not sorted in any order actually, neither increasing nor decreasing. So yeah, that's the relative values of the siblings is irrelevant. That doesn't matter. This could be less than this. This could be greater than this. It doesn't matter. But they need to have that relationship with their parent. They need both of them need to be less than or equal to the value in the parent node. So this is called a max heap. A max heap is a heap where this property is satisfied at every node. And you can easily imagine what the definition of a min heap would be. A min heap would be identical to a max heap as far as the shape property is concerned. But with respect to the heap property, the key value of the parent now is going to be less than or equal to the key value of all its children. And for the purpose of this talk, we're just going to focus on the max heap because the operations for remove min are almost identical to the operations for remove max. You just have to switch the inequality or the comparison the other way around. Now notice that uh, the largest element, yeah, what's the reason for what? Oh, that's so there's no, it's just an arbitrary choice. I mean, we could look at a min heap instead of a max heap. It's just an arbitrary choice. It's just, I mean, we could have had, I could proceed with a min heap. That wouldn't make any difference. Um, one of the reasons though, so one of the reasons I'm following a max heap here is because the textbook uses a max heap, so it's going to be relatively easy for you to read it up. And there's also a subtle reason. If you look at the heap sort algorithm in the sixth chapter of this book, you're going to realize that a max heap is going to make things a little more easier to understand because the one of the steps in the heap sort algorithm is going to be such that at the end of that sorting, you're going to end up with it's going to make things very easy. In short, you'll just see that within the next hour or so. So the short answer to your question is it's an arbitrary choice and it doesn't matter because there are two kinds of heap basically. A max heap is a heap that supports the remove max operation. A min heap is a heap that supports the remove min operation. So depending on whether your application needs a remove max or a remove min, you're going to go for a max heap or a min heap. Okay. Now the question is how, I mean, I've shown a heap as a tree here. So one natural implementation that you can think of is, having nodes and then pointers from each node to children and perhaps from children to parents also. But what we're going to do here is we're going to go for it turns out that it's much easier to implement this heap to store these items in an array. When we're going to we're going to represent this tree in an array in the following way. The first item of the array is going to be 8. The second item is going to be 6. Third item is going to be 4. So we're going to do a level order traversal and store these elements in an array according to that level order traversal. Right? So our array is going to have 8, 6, 4, 5, 1, 3. So this is our array A, which is going to store the heap in this particular order: 8, 6, 4, 5, 1, 3. And this is just empty space. So we also maintain what the number of items in the heap is, and that tells us the boundary where the heap actually ends. The length of the array itself that we allocate could be more, but effectively this is the first element of the array, this is the second element, third, fourth, fifth, and sixth. So going back to this page, this is going to be the first element of the array, this is going to be the second, this is going to be the third, fourth, fifth, sixth, and so on. And in general, if you have a tree like this, you're going to store it in this order. So you do a level order traversal and store the elements of the array in this particular order. And the reason for this is something you're going to see very soon. So let me draw that tree here again. 8, 6, 4,